Leah, would you like to start us off?
I will say welcome to everyone. I'm happy to see you all here on this Saturday morning. We have in this room, we have Joe, who's probably at the top of your screen right now. Joe, could you give a little wave so they know who you are? And we have Forrest. And I am Leah, and we'll be joined by another person from our team, Sandra. We're going to talk to you about periodic motions of a pendulum. So I was going to say thumbs up and thumbs down, but I see we have a lot of cameras off, which is totally fine. But if you are familiar with a pendulum or not, I think you're going to learn something today.
Okay, so good morning to all of you. I'm glad you're here to discover a little bit more about science. And today we're going to talk about the motion of waves. And to show that to you, we're going to use a pendulum. As Leah mentioned, my name is Joe. I'm here with Forrest, and hopefully Sandra will be joining us soon. And we work for Keysight Technologies. And waves are very important to us because electricity travels in waves. At Keysight, we build and use test equipment for anything electronic, like computers, satellites, and everything else you can think of that uses electricity. Water, heat, sound, and light also travel in waves. In fact, even the ground will move up and down in a wave motion during an earthquake from what we call the shock. So this morning we have a video to show you, but first we're going to show a few slides to help you understand some of the words we use when talking about waves. And if you stay with us for the next 15 or 20 minutes, we'll tell you how to enter a raffle to win an Amazon gift card from Keysight. So as we go through the slides, we'll take questions at the end of each slide.
And in case you missed the process for questions, just type a Q in the chat and we'll call on you. Thanks.
So good morning. Thanks for joining us. The first slide that we're showing here shows you a way that the waves can be understood and measured and talked about. And Joe gave you some examples of why waves are important. Basically, to characterize them, we speak of periodic motion, and that's a motion that repeats over and over and over again, but it repeats on a regular cycle, and it repeats over a fixed time interval. So in this first slide in the very middle, we see a representation in the very middle of frequency and wavelength. So this is two terms that are very important for periodic motion or waves. The frequency gives you how many cycles, how many ups and downs we get in a particular time interval, typically 1 second. So the little picture cartoon that we see in the middle is showing 2 cycles in 1 second. So that would be a 2 hertz wave for the frequency. And we can also characterize the wave by the wavelength. And as the little cartoon shows, the wavelength goes from peak to peak. And that distance is important for explaining what type of periodic motion or wave that we're trying to understand. If we look at the right-hand box, it's telling us that the higher the frequency, the more energy can be carried by the wave. And in the left-hand box, we're taking a little bit more detailed look at what Joe was explaining to us, that electromagnetic waves that are so important in all our lives and for the business that Keysight Technology supports is shown in the little right-hand box. And we see that an electromagnetic wave can be described as a coupled and changing electric and magnetic field. So that's on the left-hand side. Okay, So let's use these ideas for one more slide, please.
Sorry.
There we go. Yeah. So in this one, we'll give credit to NASA for putting this slide together, but it shows the wide variety of electromagnetic waves that we experience in our daily lives and how important they are, and also gives you an understanding of the type of instrumentation that Keysight Technologies provides, basically being able to measure and compare all these different types of electromagnetic waves. So our eyes are sensitive, fortunately, to electromagnetic waves, and that's what we see as visible light, the little rainbow portion of the pictorial, um, and that has a very high frequency, as it turns out. If you go to lower frequencies from visible light, you're going left in the figure, and that takes us down to radio waves, passing microwaves, going down to radio waves. And those frequencies are lower, and the wavelengths are very long. It's a little bit hard to get your orientation, but the graphic is telling you that the waves that are down in the radio portion of the spectrum, like you would get on your car radio on the AM band, are actually hundreds of meters in length from crest to crest for their wavelengths. And a lot of the types of technology that we use are down in the radio waves and then moving into the microwaves. Everybody probably has a microwave oven that they use to heat up their snacks. Our cell phones are in that same vicinity. And then as we move to the right on the figure, we will go through infrared light that is used in remote controls for televisions. I mentioned visible light that we can see with our eye. And going to the extreme right, we get very high frequencies and very short wavelengths that correspond to the types of imaging that's done in a hospital for medical x-rays, and then ultimately the types of emissions that would come from a nuclear power plant. So that's a quick summary on periodic motions. They repeat over and over again on a regular cycle, and there's just a huge variety of electromagnetic waves that are so important in our lives, as we see in this graphic. If there's any questions, now would be a good time to ask. If there aren't questions, then we've got a really nice video that Joe has put together for us on periodic motion. Take it away, Joe.
Hey, I hope you can see. Thumbs up from someone. Thank you, Leah. What we're seeing here, we're calling it a pendulum, but it actually consists of 14 pendulums. If you count the balls on here, each one of these forms a pendulum. So what's going on here is someone lifted up all these balls and released them all at the same time. So they're just starting to fall, and you can see them kind of in a straight line. So let's start this playing. And you can instantly see a nice smooth wave start to form. And if we watch it for a little bit, things will start to seem like they're getting very chaotic, but there's actually things that are going on in there that we can understand very well with electricity. All these balls swinging back and forth. If you keep watching, then you'll start to see some patterns. And so I will pause it one more time. And again, we start to see some patterns. So you might see some straight lines of, 3 or 4 balls of the same color lining up in a row. You see the yellow one starting to get together, then the green and orange, and again it moves on. And we'll just watch this for a second and see if you can detect any patterns in there.
So we have a couple questions coming in the chat. Maybe at
All
the
right.
next point to pause, we'll let them ask, but it looks like they relate to the electromagnetic spectrum slide. There's some good questions on that when we have a chance.
Okay, so let me pause this and we'll pull that slide back up and maybe Forrest will answer your questions.
I'll try. Thanks, Joe.
And I'll get the.
While you're trying to get the slide back up, one of our members of the audience was asking, where is 5G? Oh, great. So you've got the slide up. So let me take a shot at this. 5G would be roughly where oh, can you see my, yeah.
I can see, yeah, here in the microwave regions.
Microwave, a little bit lower, Joe, but yeah, in that vicinity. Yes. Mm-hmm. Very good. So that's 5G. And then the other question that I saw flashed by was X-rays that are taken in the dentist's office and how often those are saved. So all I'll say is that when I go to the dentist's office, I have terrible teeth and they always take X-rays. And so that's on a frequency of, I'd say every 6 months or so for me. I'm not going to give you medical advice, but for me, that's what happens. And the important point to remember about the X-rays in the dentist's office is they put an apron over me when they do that, and that apron doesn't allow the X-rays to penetrate and go into the body anywhere except that little region where your tooth is that they're trying to image. So that greatly aids the safety of the X-rays that they're using to image your teeth.
And then there's one, thank you, Forrest. We have one more question from a participant who I see they raised hands, and I'm going to ask you to unmute if you can.
Leah?
Oh, yes.
Well, before we get to that question, let me just add a little comment on the microwaves. If you're familiar with frequency, again, that Forrest covered at the beginning, one of the 5G frequencies that they're using is at about 28 gigahertz. And so when I say 28 gigahertz, that is 28 billion hertz. So 1 billion times a second, this thing's going up and down.
Yeah, so that's really fast. And it's a struggle. The faster they're going, like Joe is outlining, the more sophisticated your instrumentation has to be to do those measurements. And the higher in frequency you go, the trickier it becomes.
Great. Thank you.
Do you have that last question, Leah?
Yes, I think they're going to ask it.
Okay.
Could you unmute, Sine?
I already did. And it's not really a question, it's a comment. So I think can I share why the like why it goes in a way in a wave when the pendulums?
Yeah, that would be great. Go ahead.
Each pendulum, like I'm pretty sure the closest one, like the closest green one, that one, it has the shortest string, and then the next one has a bit longer and then longer and longer. And the green one, it when it moves back and forth, it goes at a faster speed than the longer strings. So it looks like it's like one of them is going slower and slower, and then it just keeps going slow, and then and then I'm not sure why it goes just out of the wave. I maybe because it's slowing down. That I'm not totally sure of, but yeah.
No, that's so good. Go ahead, Joe. I was just going to say quickly that Joe is got a whole little explanation coming up on how he designed the setup of 14 pendulums, and we were going to go through a little bit of how you get this fast and slow oscillation that you were just talking about. So that's super good setup for what Joe's going to explain to us later.
Now, I will jump ahead a little bit and talk about one of the things that you said. Is it Sine? Is it the
It's pronounced Sine.
Sine? Okay. Anyway, Sine, one of the things that you said isn't quite right. Is actually because we lift up all the balls together and we drop them all at the same time, gravity is what sets their speed, right? Does that make sense? And so they're all actually falling at the same speed, or they're actually all moving at the same speed, but they appear to be that some balls are moving faster than the others because the balls on the shortest string only have to swing a short distance, and the balls on the longer swings have to swing a long distance. And so they're all traveling at the same time, but each ball takes a different amount of time to go all the way, swing all the way up, come to a stop, and then swing all the way back, come to a stop, and so on, go back and forth. But they're actually all traveling at the same speed, or they should be if they were dropped properly. But gravity is what's setting their speed. All right, so let's go back and look at our video again. And we'll let this run just a couple seconds, and then you'll see someone actually come in and start the thing over again. And now you can see how they lifted up all the balls and let them go. And if we watch on this side, in a few seconds, you'll start to see some patterns. And this, it's easy to look down here and you, for a moment, see the sine wave motion, but then it appears to get chaotic. But as we move on in time, in a second here, you're going to see that watching on the side, and all of a sudden you'll see just the orange balls, and then just the green balls, and just the yellow balls. So they've all become aligned. And there's all green, all yellow, purple, orange, green, yellow, purple, orange, and so on. So, all right, so I will let this go for a moment. Try to get caught up in my notes. So one of the things I will point out is when we're watching this video, you can probably tell that it's been greatly slowed down. The person using the camera set this into slow motion so that we can actually see this and follow it. Because if we were going at full speed, everything happens really, really quickly, and it's hard to see some of this stuff. So we slowed it down. So if you were trying to guesstimate, or make some estimates by counting the number of swings, it won't actually be in real time because the video is kind of distorting the time for us. All right, so anybody? Go ahead, Leah.
We have some really good questions pouring in here.
All right, let's
I'll
pause
read
it.
I want to read you the first one. So if those 14 balls in the experiment had the same length of string and same speed, would they be moving at the same time?
Yes, and you've probably all seen the little versions of this that are made for desktops. And a lot of those, ours is swinging left to right, from our picture, ours is swinging left to right, but a lot of those that are made for desktop swing end to end where the balls bang into each other. But the ones that are made to swing left and right, if they all have the same length of strings, then you would just have two lines of swings forming. And they should, as long as the string lengths are correct and the weight of the balls are all the same, they should always stay in a straight line. And of course, gravity and friction, not gravity, but friction is one of the things if we didn't have any friction, if the balls weren't moving through air and we're getting a little bit of air resistance at the top of the fixture where the strings are attached, the strings are kind of rubbing as they swing back and forth, and that causes a little bit of friction. So that's what slows it down. If there wasn't air resistance, if we did this in a vacuum, those balls, and there wasn't friction at the top, those balls would swing forever, and we'd just over and over again see these patterns emerge and then break up and then come back and on and on.
So next question is, do we know the frequency of electrons, the wave particle duality?
Yeah, so I'll try that one. I would say that the electrons can have a variety of different frequencies depending on the energy. And then that was the point of that very first slide we showed, where over on the right-hand side, it was showing the higher the frequencies, the more energy is carried by the wave. So they can have a variety, as the person is pointing out. There's a wave aspect to electrons, and they can have a variety of frequencies and corresponding energies.
If you took an electron and you cooled it, made it very, very cold, colder than even space, its motion would almost stop, and it would be at a very low frequency. If you heated it up, if you really got a lot of energy into it and it heated up, it's going to emit light, which is going to be at a very high frequency. So yes, it all depends on the amount of energy that's within the electron.
These are great questions.
Yeah,
Thank
great.
you all.
It looks like
Very-
Sinan was raising his hand too, Leah.
Yes. Yes, thank you. I see that. I was trying to go in order. Sinan, if you can wait one more second, I want to get to the next question from Harshu. What is the constraint that is making them move in different places?
Well, they're actually, it's just the different string lengths.
Right.
Now, I
Yeah.
will mention that one of the things that I discovered when I made this was that if I used a single string coming down to the ball, then you had to be super, super careful when you let go, or else the balls would move sideways and bang into each other, and then you'd really see chaos. But by doubling up the string, I'm still using the same length from the top to the ball, but I've used two strings and attached it in a slight V, and that keeps the balls from going from side to side and hitting each other.
Great, thank you. All right, Sinan, we're ready for yours. If you could unmute.
So, if all the balls are the same, would the matter, like the air? Because if all the balls were the same weight and different and the same strings, like the same size string, but one of them had holes in it, would that matter? Like, would it slow it down?
Well, if they're in air, yes, because the weight of the ball, can overcome the air resistance, overcome some of the air resistance. And so it'd just be the same as you had, if I put one of these as a wiffle ball, it'd be easy to blow on that ball and mess it up, and so yeah, that's important, to keep these things lined up, that they all have essentially the same weight, or what we call mass. They all have the same mass, and it is affected, their speed is affected by their mass.
Thank you. Great question. Now there's one more question. I think we missed the context, but the question was, absolute zero is formed by that, right? And I don't know the time at which that was asked, but Joe or Forrest, does that make sense to you?
I think the person is probably referring, with the electron, yeah. So Nicole was saying with the electron question, Joe was referring to temperature, and if you cooled, the energy would be lower. And then I think Nicole was reminding us, gee, what if it went all the way to absolute zero? So conceivably, if you got to very close to absolute zero, the motion would be very small. and the energy would be very low.
Okay, let me start this video again, and let me see where I'm at in time. Okay, so this will run for about a minute, and we can continue to talk about questions or whatever, and then we'll get a new release. And I will ask, is anybody wonder why I made this in a triangle shape? Can anybody tell me why this should be in a triangle shape? The reason is, triangles are very, very stable. If you look at bridges, and oftentimes you'll see bridges are made with shapes of triangles, because triangles are very strong and they're very stable. If I just had one pole sticking up on each end, as soon as I brought all the balls to one side and let them go, that's a lot of mass. That's a lot of weight that's going to cause the thing to tip over. And so by using a triangle, that keeps it from tipping over.
Yeah, Joe, Nicole had put in a little chat message that said triangles are sturdier. So it looks like she got that one nail on the head on that one. Yep.
Great job, Nicole. Yeah. All right. So this has just been released again. And again, we'll just let it run for a moment. See the nice patterns. And again, at this point, we'll let it run for a bit. And anybody else has got some questions, that was a good time.
Oh, that's a good question we have from Mariam. If all the balls were a little heavier, would the pattern still be the same?
Yes, it would. And actually, what got me started on this was I saw something on the internet of somebody did this with bowling balls.
Oh boy.
And that was a really cool one. They did a lot of bowling balls too. They did it outside, and it was a really cool one. But when we built this for actually having people show up at the fairgrounds for Science Discovery Day, we couldn't have a bunch of small people running around with bowling balls swinging on strings. So this is a little less dangerous. Again, right here, you kind of see almost two lines. The ball's going in opposite direction. There's just one more pattern that's showing up. Now, if pause this for a second. Oops, I missed it. Let me go back a little bit and pause that. Sometimes you see some balls that don't look like they're quite in sync. And if we look at the top here, I have a row of hooks there with what are really screws and nuts on there. And so then I can actually, because the string lengths have to be very, very exact, I can actually adjust those hooks at the top, up and down just a little bit to make sure they're all in time. And of course, everybody knows about COVID-19. So this thing is far away from me, and I haven't had a chance to have my hands on it for more than a year. And so there are some things that are slightly out of time.
So 2 more questions coming in. The first I want to say to Sinan, yes, Joe made that pendulum a couple of years ago, actually, in 2017. And we've used it at North Bay Science Discovery Day for, this might be our 3rd year. But before that, we have a question from Nicholas to everyone. What if we used small, medium, and large balls at the same time?
I might have to think about that one. It's a good question. I know one thing, it would look funny because we'd have to space the balls, at different intervals, and so it wouldn't look like a smooth line. And the one effect that you'll have is, again, because if we use large balls, and presumably they're heavier, but even if they're larger, they're going to see more wind resistance or air resistance. And so their motion is going to be slowed differently or affected differently by, due to their size. And so that would actually kind of break up the patterns.
Yes, and Mariam had that thought and answered that, yeah, if the balls were different sizes or weights, that the shape form would be lost because the bigger balls would swing. Well, they would swing at different rates, certainly.
Right, and here, looking at it from the side, we can see the curve moving down. And if you watch for a second, it almost looks like the curve is traveling down the line. And that's exactly what happens in electric waves. As they're traveling down wires, the magnetic field and the electric field. Anytime you have electricity, you're going to have an associated magnetic field. Anytime you have a magnetic field, you could actually use that to generate some electricity, which is what they do with generators. And the wave travels down the line. Or we say that it travels down the line. It looks like this. And we just watch this for a little bit, and then now I don't know how it looks on your screen, but it almost looks like the balls are popping straight up and down on my screen. I think it's kind of a cool look. It's not real, but it looks that way.
Do you want to talk a little bit about how the pendulum was made in our last 12 minutes here?
Sure, we'll get that. And I did want to just real quickly, if you watch the balls on the two end, like the yellow ball on the right side and the green ball on the left side, you can kind of really see that they are traveling at the same speed, but the yellow ball has to travel much farther. And so, the green ball has more swings in a given amount of time, but the yellow ball is traveling at the same speed. And so, at the bottom where the ball is moving, we describe that as an arc, a curved line. And so each ball is making an arc, and that the length of that arc is how far the ball is traveling. And so so what happens with all of these balls is every once in a while, and an easy way to think about it is that if, say, one ball had to travel about 10 inches and another ball only had to travel 2 inches, then let's say the yellow ball, it swings out and back. So it goes out 5 inches and back 5 inches, and then it's traveled 10 inches. Now, if I took the green ball and it's only moving 2 inches, then 2 times 5 is going to be 10 inches, right? So it's got to go 5 times, but 5's an odd number. And so if it starts on one side, goes out, comes back, goes out, comes back, and then goes out again, that's 5 times. And so it's going to be on the opposite side. And that's how the balls, at that point in time, they're not lined up. But if we go another 5 swings, then the yellow ball, again, 5 swings for the green ball, sorry, it's going to move another 10 inches, and the yellow ball is going to go 10 inches. But at that point, both of them are going to end up at the same side, right? Because they both travel 20 inches. 20 is an even number, so they're both going to be on the same side, and that's how they get aligned. And the same effect happens with all the purple balls or all the green balls. Is after so many swings, mathematically, swings are, the number of the distance that they have traveled in so many swings is equal, and then they all of a sudden they look like they're lined up, but they continue to swing, and then they immediately get out of sync again until they hit another multiple where they're lined up again. So and when we say they're all lined up in electronics terminology, when we say everything's lined up. We call that being in sync or synchronized. So let me get a control of my mouse, and I will switch us back to our slides. And we can talk about this if you like, or if we have questions.
Maybe, Joe, if maybe just describe how you made the lengths of the string, Joe.
Okay, so yeah, this is a lot to read, so everybody doesn't worry about it. Originally, I wrote this up as a handout, so if you came to our booth at the fairgrounds, you could take this away and look at it if you were interested. And so it's quite a bit to put on one slide. But essentially, when I started this, I had to do some calculations, and I just chose a number. I said, I want the first ball to swing 51 times in 60 seconds. And there's a formula that tells me how to use this formula to calculate the string. And so the second ball would make 52 swings in 60 seconds, the third ball 53, so on, all the way up to the last ball would have to swing 64 swings in the same amount of time for the 14th ball. So, oops, I'm sorry. I switched to a new mouse and I'm not quite used to it. So let's just talk about this briefly. As I mentioned before, gravity is what pulls the balls towards the ground. And on Earth, there's actually a formula that tells us, how fast gravity will pull something towards the ground. And on Earth, that is 9.8 meters per second per second. And when I say per second, it's because it speeds up. And anything that speeds up, we call that acceleration. And since the balls are traveling in an arc or a curved motion, part of a circle, we have to use a number that you may have heard of. That number is pi. And so I just put all that into the formula, and it actually gives me the length of each string. And I had to do that 14 times. When I got all done, the numbers that I came up with were fairly short strings, and this thing would be small. Something could fit on a desktop. So I didn't want to do that. So I just doubled all the lengths to make it so I can make it, much bigger display. And one of the things, if you look down the length of the pendulum, we see the thing start off in a straight line, and it pretty quickly forms a nice smooth curve called the sine wave. And later on, when we see the patterns where the green balls are lined up or the yellow balls are lined up, in electronics, we would call those harmonics. And but scientists, engineers, and technicians all must understand waves to make use of them for power in our houses, music, cell phones, TVs, and computers. Questions?
We're so grateful, Joe, that you did all these calculations and made such a great demonstration for us today. And then at the very top of this page, Joe is acknowledging the guy that first figured out how these objects would fall due to gravity, and that was Isaac Newton. So a big shout out to Isaac Newton for providing us with the theory for how you'd go about making the demonstration.
Okay, if we don't have any questions, let me pop this up here. You want to write this down, you can go to keysight.community@keysight.com, enter a raffle to win a gift card.
So Joe, there's another question here from Sana to everyone, which is a really great question. For the equation 4 times pi to the second times frequency to the second, am I saying that right? 4 times pi to the second power times frequency to the second power. Why do you multiply by 4?
Oh, 4 comes into the formula for working with circles. I don't have that written down here, but But actually it ends up, what it really ends up is that the number 2 is in there, and the number 2 squared is 4. So each of these terms are actually squared. And it has to do with, in a circle, there are 2 pi. We say that the circumference, the length of the circle, the outer length of the circle is related to 2 pi. And so when we have 2 pi in here and we square 2, we get 4. So I took the, as Leah mentioned, pi to the second power, or actually we would just say pi squared, a shorthand way of saying it. Pi times pi, and frequency times frequency, and 2 times 2. But instead of writing that in there, I just changed it to 4.
It's another great question.
Yeah, it really is.
Yep.